Welcome back for another round of chemistry. Boy, you just love the punishment of ultimate chemistry. Well, here we go. 3.07, the gas laws. Now, everything we do today is going to assume that we're working with ideal gases. And remember, at STP, we can assume that gases are behaving enough like ideal gases for us to make use of this math. Here's a story. There are certain properties that a gas has, and regardless of the gas, we can change these as variables. Avogadro's hypothesis says that all gases can be treated the same, because if you have the same conditions of volume, temperature, and pressure, then you can assume you have the same number of moles of molecules. Mole is just like a way of saying dozen. So it's like, instead of saying I have 12 eggs, you can just say I have a dozen eggs. It's a certain amount of eggs. A mole is just a much greater number. Now, volume can be measured in milliliters or liters. It doesn't matter which you use for the purposes of this math. And pressure can be in atmospheres, kilopascals, millimeters of mercury, torr, whatever. It doesn't really matter. However, temperature can only be in Kelvin. So if you have a Celsius temperature, you must convert it to Kelvin first, because we need absolute scales to do this math. So if it says that the gas is at 0 degrees Celsius, you have to convert that to 273 Kelvin before you use this formula. All right. So the only thing that absolutely has to be a particular unit is temperature. Temperature must be in Kelvin. Now, moles we'll deal with next time. So don't worry about that for right now. This right here is Robert Boyle. Boy, I wish I had hair like that. Now, actually, I just wish I had hair. Now, as the pressure, which we'll call P1, of a sample of gas with a volume of V1, if we increase this pressure to P2, the volume of the gas will decrease to V2. See my music video called Squish. Basically, gases are compressible. So if you increase the pressure, you'll decrease the volume. And what's more, if you double the pressure, you'll cut the volume in half. This right here is what's known as an inverse relationship. Jacques Charles did the experiment that determined that gases expand when you heat them. If you increase the temperature of a gas, its volume will increase as well. This is a direct relationship. Not only that, but if you double the temperature, you'll double the volume. And this relationship became known as Jacques Charles' law. The temperature, by the way, again, must be in Kelvin. Cannot reiterate that enough. Finally, Joseph Louis Gay-Lussac realized that if you take a gas in a sealed container that cannot expand or contract like a gas cylinder, and you heat it up, the pressure will increase. So if you increase the temperature, the pressure will increase. Not only that, if you double the temperature, the pressure will be doubled. And once again, the temperature must be in Kelvin. So we've established the relationships. Pressure and volume are inversely related, but both are directly related to the temperature. And this leads to a gas law called the combined gas law. The combined gas law, which combines Boyle's law, the inverse relationship between pressure and volume, Charles' law, the direct relationship between volume and temperature, Gay-Lussac's law, the direct relationship between pressure and temperature. If we combine all of these together into one gas law, we get one combined gas law, which is why it's called the combined gas law. And you can find this on New York State Reference Table T. You'll take a look at Boyle's law, P1V1 equals P2V2. Well, there it is. P1V1 equals P2V2. Charles' law, V1 over T1 equals V2 over T2. Well, there that is. V1 over T1 equals V2 over T2. We have Gay-Lussac's law, P1 over T1 equals P2 over T2, and there it is here. P1 over T1 equals P2 over T2. So all three gas laws combine together to form one easy-to-use formula. Now, if any variable is held constant, like let's say the temperature remains the same, it will just cancel out, so you can ignore it. So if it says at constant temperature, just get rid of temperature and you get P1V1 equals P2V2. If it says pressure is constant, then it's V1 over T1 equals V2 over T2. If volume is constant, then it's P1 over T1 equals P2 over T2. If nothing is constant, then just use every variable in the formula. First, rearrange the equation, then substitute, then solve. Now, for my classes, I am not going to accept just simply plugging the numbers into this equation. If you want to solve for V2, multiply both sides by T2, divide both sides by P2, and then plug in the numbers. Okay? So, here's a simple problem. We have a 5-liter sample of gas at STP. The temperature is 273. The pressure is 101.3 or 1 atmosphere. Has a pressure decreased to 0.5 atmospheres at constant temperature. So temperature will remain constant. What is the new volume of the gas? So we have P1V1 over T1 equals P2V2 over T2. We're going to rearrange it to solve for V2. But before we do that, we're going to eliminate T1 and T2 because temperature is constant. This is the new rearranged equation. Go ahead and do the algebra for yourself. Then all you have to do is just substitute in the numbers. Atmospheres will cancel and leave you with liters. You do not have to learn new math to do this. You just have to rearrange your equation, substitute and solve, and temperature is not part of the equation because it's constant and would just cancel out. Charles' law. A 5-liter sample of gas at 300 Kelvin is heated to 600 Kelvin at constant pressure. What will the new volume be at that new temperature? Well, the pressure is constant. Therefore, we can eliminate P1 and P2, leaving us V1 over T1 equals V2 over T2. Now, rearrange to solve for V2. Multiply both sides by T2, and you'll get that. V2 equals V1 T2 over T1. Then just substitute in your values and solve. The units for Kelvin will cancel, and liters will be the unit that's left. Here's a Gay-Lussac'S law problem. A cylinder of gas. Now, gases in a cylinder, cylinders are typically made of metal, and this metal is very strong. So if you increase the temperature, you're not going to be able to expand the cylinder. The cylinder will remain rigid. Therefore, the pressure will change. So when you solve this particular problem, you're going to assume that volume is constant. So you get P1 over T1 equals P2 over T2, rearrange to solve for P2. So multiply both sides by T2, and then just substitute in the numbers and solve. Now, it's very important to put the temperatures in the right place. T2 goes on top, so 600 goes on top. T1 goes on the bottom, so 300 goes on the bottom. The units atmospheres cancel, and this here should have been Kelvin, not liters. That was a typo on my... I swear, if I was a superhero, my name would be Captain Typo! But I'm not a superhero, so it's not. All right, what if we combine all these gas laws together? So we have a 3-liter sample of gas at STP, which means the temperature is 273 Kelvin and the pressure is 1 atmosphere. And again, if you forget this, just look at the front page of your New York State reference tables. Nothing is held constant here. Everything changes. So we leave the formula the way it is. We rearrange to solve for P2. So we divide both sides by V2 and multiply both sides by T2 so that we end up with this rearranged equation. Then just simply add the numbers in. We have a pressure of 1 atmosphere, so 1 atmosphere. We have a volume of 3 liters, so we put that in. A temperature of, well, it's at STP, so, well, this says T2. Ha ha ha. So that's 546. I almost got caught there. The new volume is 4.00 liters, and the starting temperature, that's the 273. So we plug in the numbers, and what will happen is that liters will cancel, kelvins will cancel, and leave you with atmospheres. And remember, if you plug this into your calculator, 1 times 3 times 546 divided by 4 divided by 273. Just put in your calculator in one swell foop or one fell swoop, whichever you prefer. And then, of course, significant figures, 3, 3, 3, 3, 3, 3. We put the 0 at the end to make 3 significant figures. Here's the next example. We have a 4-liter cylinder of gas at 100 kilopascals and 300 Kelvin. We're going to double the pressure. What temperature do we have to heat the gas to, assuming the cylinder doesn't burst? What does this tell us? That the 4-liter cylinder will still be 4 liters when we're done. Since the volume will be 4 liters for V1 and 4 liters for V2, they'll just simply cancel out. So we'll have P1 over T1 equals P2 over T2. We want to solve for T2. So we want to get T2 out of the denominator, multiply both sides by T2, divide both sides by P1 until you get this formula here. You could also have rearranged it, left T2 in the denominator, and then just taken the reciprocal of both sides. Either way you want to do it is fine. Then you just substitute in the numbers. We have P2. Now, what is double 100 kilopascals? 200 kilopascals. T1 was 300 Kelvin. P1 was 100 kilopascals. We can just ignore the 4 liters because it's going to be constant. And when we substitute the numbers in, atmospheres will cancel and leave us with 600 Kelvin. And again, 3 sig figs, 3 sig figs, 3 sig figs. We want 3 sig figs in our answer. So you do not have to relearn math to do gas law problems. It's exactly the same math you use to solve Q equals MC delta T. It's no different. You just algebraically rearrange the letters first, then substitute in the numbers, and then pop out an answer that's correctly rounded with a unit. And notice when I show my work, I include the decimal point for the pressure. I include the decimal point and the decimal point for the pressure and the Kelvin. So I don't lose track of my sig figs. I include the units when I substitute the numbers in. Make sure you do that, and it'll be a lot easier for you to keep track of what everything is, canceling your units out to make sure you have the right answer. And that is how to do gas law equations. Now, next up will be the ideal gas law. PV equals nRT. But until that time, I await your arrival once more, even though we've probably never met unless you're in my class, in which case we likely have. And until next time,